Okay, welcome to the last talk of this session, given by Professor Sudhansu Mandal, IIT Kharagpur, and he's going to tell us about a novel phase of U plus 5 half.
Sorry. So first of all, I would like to thank the organizers for inviting me to give a talk in this nice conference. Okay, so the title of my talk, this is a novel phase of 5/2 filling factor. So usually we know when I talk about 5/2 filling, we know usual phase called Pfaffian phase, anti-Pfaffian phase, or particular Pfaffian phase. This is much talked about. So, but what I will tell you today, there is a novel phase which is orthogonal to all those three phases. This is a novel phase, and hopefully I will able to convince you that the experimental regime corresponds to this novel phase. Okay, so these two graduate students who worked out this problem. So she is already graduated, and he will be soon graduated. Okay, so 5/2 state was discovered way back in 1987. At that time, it was surprising, but thanks to Moore and Reed, so we had some knowledge about the 5/2 filling factor since then. And later, the second Landau level, a lot of second Landau level states are also observed in 2010, and also there are some experiments later on. So as you can see that the filling factor half in the is one of the most prominent states in the second Landau level. So we will talk about only the states in the second Landau level, especially for 5/2 states. And you know that the states of sequence are not in the sequence of lowest Landau level, which we know are the Jane sequences or composite fermion sequences, which are observed for lowest Landau levels. But these sequences are different from this usual lowest Landau level sequence. Okay, so thanks to Moore and Reed, so we had understanding about 5/2 filling. So in terms of electron operator, which is the charged bosonic operator and a neutral Majorana harmonic operator. So by doing CFT, they proposed a wave function which is called Pfaffian wave functions, because this function is Pfaffian. So you have a Zi minus Zi square, so you can think about it's a composite fermion, and those composite fermion has some chiral px plus ipy wave pairing, and that gives you a Pfaffian function. So that was the Moore-Reed wave function that we know. And one thing to see here, it is non-zero even when two particles coincide, but it vanishes when three or more particles coincide. So, but that is not true for Laughlin or any Jane states, where actually if you have two particles at the same positions, the wave function vanishes, but not for these Moore-Reed wave functions. In fact, for any non-abelian wave functions, this has to be true. So at least two particles may coincide. But for this wave function, it vanishes when three or more particles coincide. And this pairing causes a bulk gap, and bulk case correspondence provides a neutral Majorana mode coming from this operator, and along with the bosonic charge mode. And it also predicts non-abelian breeding statistics of quasi-particles. It predicts a quasi-particle charge E/4 instead of E/2, which one can think about, because filling factor half, from Laughlin's consideration, one can think of E/2, but actually the E/4. And then there was an experiment to observe the quasi-particle charge. So this is in short noise experiment. So that was kind of set up for observing 1/3 or 1/3 state. So there is a possibility of tunneling of this quasi-particle that hits the noise, and from that slope, it was observed that it actually the quasi-particle charge is E/3, similar experiment has been done for 5-half state, and it was more or less, it was consistent with the charge E/4 rather than E/2. But so there are a lot of theoretical debates. So actually the fractional charge E/4 can be predicted from several other models, including the abelian theory of 5-half state. So, but from the non-abelian class, which one believes for the 5-half state from the prediction of Moore-Reed-Pfaffian. So there's one candidate state is Moore-Reed-Pfaffian, and there is another proposal, it's the particle conjugate of that state, which is anti-Pfaffian, because that is degenerate with its pure two-body Coulomb potential. Actually, these two states are degenerate. But however, the degeneracy is broken when we include three-body interactions. But the energetically, they are very close, so hard to predict that which one will be actually wins in actual system. So that was a strong debate between Pfaffian and anti-Pfaffian, which will be actual phase for the 5-half state. Then another candidate state was proposed, which is called particle Pfaffian state. That also predicts Majorana mode. So all these three kinds of theories or the phase what you can talk about, Moore-Reed-Pfaffian, anti-Pfaffian, and particle Pfaffian, all of these actually predict Majorana mode. But to distinguish that, one can measure thermal Hall conductance, because that gives some different predictions of thermal Hall conductance. So if I believe the Pfaffian state, so it has two states, because two completely filled Landau levels, there are two propagating modes, and the one quasi-particle mode, and there is another Majorana mode. And the Majorana mode carry the half unit of thermal conductance. Other modes carry 1 unit of thermal conductance. So the Pfaffian will predict 7/2. If you have an anti-Pfaffian, it turns out it will be 3/2. But if you have the particle Pfaffian, then there is 3 and there is a minus half, so it predicts 5/2. So there is a clear distinctions between the predicted value of thermal conductance from these three phases. And so the experiment was performed in 2018 in Weizmann Institute, and those are the predicted different kinds of theories can predict different kinds of edge modes and the corresponding thermal Hall conductance. But what they found is that more or less it is 5/2 in the unit of thermal Hall conductance. So it suggests that particle Pfaffian topological order rather than Pfaffian or anti-Pfaffian. There is a strong debate after this experiment. So theorists believe that it will be Pfaffian or anti-Pfaffian. They more or less ruled out the particle Pfaffian, but the experiment was just opposite. The experiment was suggesting the particle Pfaffian. Okay, so between debate between anti-Pfaffian and Pfaffian. So again, the Weizmann group had short noise experiment. So here what this is that is a 5-hour state, and there is a filling factor 3 if they sandwich these two filling factors 3. And if you believe particle Pfaffian kind of pairing in 5-hour 2 state, then there is a cancelling about these modes, but you have 2 more modes are there because they are counter propagating, and that creates noise. So you will predict it should be noise if you have particle Pfaffian. But if you have an anti-Pfaffian, so there is a cancelling out both the modes in the same direction, so you don't predict any noise. But they have observed noise in the setup. So so it kind of one more confirmation that you have particle Pfaffian order for 5-hour state. But most theorists do not believe that. According to them, it will be either Pfaffian or anti-Pfaffian, mostly numerical calculation actually suggesting that it will be anti-Pfaffian. Okay, so here is my motivation. So why did I my work? So there is no clear understanding of experimental results. And if you see the numerical studies are generally relatively low values of Landau level mixing, because Landau level mixing can generate three-body interactions. It is generally less than 1. While the experimental systems typically have the value of this parameter, Landau level mixing parameter, which is the ratio between two energy scales, Coulomb and the cyclotron energy scales. For the typical experiments in gallium arsenide, it is between 0.8 to 2. So most of the theories are well below 1 hydrogen charge. Only few theory has been performed, calculation performed near about 1. So they did, the effective Hamiltonian they have found. So there are 3 terms that we are talking about here. This is the two-body pseudo potentials if you have the second Landau levels coming from the Coulomb interactions. But if you consider Landau level mixings, because these 5 have typically not very high magnetic field, so there is a possibility of Landau level mixing. So that can cause both two-body interactions as well as three-body interactions. So if you consider these corrections in the linear order of kappa, so they have actually found out the values of delta Vm2 and Vm3. And then these people have done study here. So if you see that there is a overlap Moore-Reid Pfaffian state, and if you vary the parameter kappa, actually if you take the overlap of the exact state and the Moore-Reid Pfaffian wave functions, it actually it's drastically changes to 0 and near about 0.7. And that happens also for anti-Pfaffian. So anti-Pfaffian, and they, according to them, actually Pfaffian wins, but there are some later calculation actually say that the anti-Pfaffian wins, but nevertheless, both of them actually vanish. But they go beyond that, and they kind of see something non-zero here. So they predicted their possibility of some new phase, but they didn't have any understanding about that phase and what is that new phase that was not talked about much. So we take this weapon. We went beyond this value of kappa, and so there's a disclaimer that unless we are considering energies of two competing states, moderate kappa may still be used for certain qualitative physics, because the kappa is done perturbatively, and actually these values are not very large. So even if you take kappa square, unless you compute energies between two competing states, you will be more or less valid. If kappa is not very large, maybe in kappa order of 1, it's okay. So here is our calculations. So what we did is we did exact diagonalizations at different values of kappa. And so we considered the three-body pseudopotentials up to angular momentum less than 8. And if we see that, so if you are doing calculation in sphere, if we see that the ground state at 0 angular momentum, then we take overlap between two ground states at different kappas. So that is the overlap. So that is our 3 fixtures. You can see here different particle numbers and different flux. So these particle numbers, these flux correspond to the Pfaffian flux. We are not saying the Pfaffian phase, we are saying the Pfaffian flux. And here this is anti-Pfaffian flux, and here particular Pfaffian flux. So because this is actually, this 2q flux is 2n minus 3, and this is 2n plus 1, and this is 2n minus 1. So they are called Pfaffian, anti-Pfaffian, and particular Pfaffian class. So all these 3 types of flux shifts, what we did is these calculations, you can see that at the low kappa phase, so there is, so for different ground states are, so almost you can see that the overlap is close to 1, close to 1. But then if I near about 0.7, we don't have any quantized state, just as before I described others' work. But then if you go beyond that, you get another quantum phase where again, at different kappa, you have the overlap 1. So there is a clear topological phase transitions from one phase to the other. So the so our theoretical understanding so far actually for this phase, but we have found another quantum phase here, which is at moderate kappa. So you find this phase. Yeah. No, kappa I, kappa j. At different kappa, you are talking about taking the overlaps. So your ground state at kappa 1, ground state at kappa 2. So if you have the same ground state, so if you describe that physics with the same ground state, so there should be close to 1. Okay. So you find one ground state at lower kappa, another ground state at higher kappa, and they are orthogonal. And you find a topological phase transitions across some regime. Okay, so at this moment, so I want to talk about another experiment. This experiment of Pardu's group. So they have measurement of resistance at x directions and y directions, so RXS, RXY. So they find and they change the pressure, and what we can see that here it is fractional quantum Hall state because RXS and RXY are almost same, but if you change the pressure and at some point you find a pneumatic phase where RXX, RXY are different, you can see that one case is peak, another case is valley. So there is a pneumatic phase, and that was their regime. So here you can see that there is a pneumatic regime here, but so if pressure is low, then you have a fractional quantum Hall state. So they had correspondingly density here from corresponding pressures, corresponding density, then have a corresponding magnetic field, and then from there they actually found what could be the kappa value and see that the transitions occur at 5/2, and this phase is up to 3, and you see that the fractional quantum Hall states observed is less than 2. So quantum Hall state is observed for less than 2. That's what these regimes are less than 2. But what we're saying is that at some point there is a phase transitions and go to the lower k phase that is not being observed in experiment. All right, so we have found a new phase, and so we characterize that phase proposing some wave function. So that is our proposed wave function. So if I do not consider this symmetrization factor, so we can say that it's a Halperin 113 state, but actually it's not Halperin 113 state because there is a symmetrization. Because if you consider Halperin 113 state, then the particles will have 2 species. But these particles are not of 2 species, the same species, electrons. But you can describe these wave functions like this. So if you have a factor Zi minus Zj, you can think about some kind of bosons. And the bosons actually made two groups of bosons, but there is no physical segregations. And then intra-group non-interacting composite boson, there is no repulsion between intra-group bosons, but there is a inter-group repulsions that can be read out from here, Zk minus Zl square, so that fills 2 zeros at each other positions if the 2 bosons corresponds to 2 different groups. So that group can be formed by any n by 2 out of the n electrons. It's not that you have phase segregations like Halperin 113 state because there is n by 2 one species and there is another n by 2 one species, other So this is it's not Halperin 113 state because of this symmetrization factor. And how good is this wave function is? So this is the new phase, what we call it A phase. So this is the low K kappa phase. If you take the overlap of Moore-Reed wave function or particle conjugate of that wave functions and corresponding ground states, to take the overlap of these wave functions with the corresponding ground states, you can see that those things actually decreasing with kappa. And so this regime, there is no quantum Hall state. After that, again quantum Hall state, but the wave functions overlap with those things are 0. But if I consider these wave functions, for the lower phase, it is 0, but in this phase, it is very high overlap. It's more than 90% at any kappa. By the way, so our trace actually beyond this value, maybe 1.6 or 1.7, we don't find quantum Hall regime. So this is the only regime. So between this to this is a quantum Hall regime. Beyond that, it's not quantum Hall regime. Maybe that is the pneumatic phase that Pardu's group have found. So, so that is the nice large projections with the exact ground state that we have found, but we have also calculated the entanglement spectra for these wave functions and compare with the exact ground state. You can see that the low energy branch quite have good, very good match. So the conclusion is that the proposed wave functions captures the topological order of the state, the new phase. So, okay, so this is my wave functions. So if I see the power of those Zi minus Zj, then I can, long wavelength physics, we can have the, we can do the Chern-Simons theory for the A's. So the K matrix becomes 1, 1, 3, 3. And you can, because the symmetry matrix, you can have charge vector 1, 1, quasi-particle vector 1, 0, and so on. So you can, it gives you the filling factor half that we want. It gives quasi-particle charge 1/4. If I consider the S vector half, it also gives the topological shift 1, which is actually there in the state. And the eigenvalues of this K matrix is one positive and another negative. So the central charge is 0. So that means one forward moving mode, another backward moving mode. Both have the charge 1/4. So altogether, what we have the modes here. So these two modes are for the electronic modes because two Landau levels are completely filled. And then there is another mode, forward moving, quasi-particle charge U/4, and that can carry thermal Hall conductance 1, like the electronic mode. And then you have another mode, which is backward moving, will have charge minus E/4, the kappa also value 1, thermal conductivity 1. And there is another prediction here. So it's not the rigorous. What we're saying is that in these wave functions, any n by 2, I mean, there are n composite bosons. So, and there are two groups. So any composite bosons can occupy any of these groups. So there are kind of hidden Z2 symmetry is there to occupy those groups. So that may lead to some kind of Majorana mode, and that can give you thermal conductance. So in total, it can also predict, this wave function also can predict this 2.5 unit of thermal Hall conductance. Okay, so we had a description of our 5 of our state, but you have in second Landau level, there are too many states. So what we have done is we have generalized our proposed wave function, this one, further. So if I have this kind of form, so what we can find is the filling factor n/nm-1. And you can see that all those filling factors that have been observed belong to the sequence n/nm- minus 1, where n greater than equals to 1 and m greater than equals to 3. And also 1 over 1 minus nu, those are particular conjugate states of these filling factors. So we have done similar things as I described for 5 over half state. And for different states, you can see that again, we see the new phase, the A phase that we're talking about for all those states, and the overlap of those states with our proposed wave functions that has a good overlap, always more than 90%, sometimes close to 100%. So for all those states, you can see that half, 2/5, 3 over 8, those are all observed states, 1/3, 2/9, 1/5, 2/3, 7/9, 4/5, for all those states has been in that regime. And as we described for 5 over states, for similar way, we can also work out for S modes. So this is the S mode for half state that I described. So these two modes are for fully filled Landau levels. And there is a E over 4 minus E over 4 forward and backward moving, and one Majorana mode for half. So if I go for 2/5, so you have E over 10, E over 10, 2 forward moving and 2 backward moving minus E over 10 minus E over 10, and one Majorana-like mode. 3 over, okay, so 2/5, 3 over 8, there are 3 forward moving E over 16 charge, and minus E over 16, one forward moving mode, Majorana mode, and so on for other states also. So you can see that, so total thermal Hall conductance that it can predict, so 1 unit here, 1 unit here, 2 unit, and for every case, actually there is a cancellations. So this thing, forward and backward cancellation, there is only half unit for Majorana mode. So in total, you have 2.5 for all these states in second Landau levels. So we predict 2.5 unit of thermal conductance for all states in the second Landau level, not only the 5 half state. For all states, it's 2.5. So this is the conclusion. What we find is that re-entrant anomalous quantized phase, which we call A phase, for 5 half quantum Hall state. And that is in moderate strength of Landau level mixing. The range is 1 to 2. About, it's not exactly 1 to 2, it's in order. So, and this proposed wave functions with particular symmetric Haffian flux shift, although it's not particular, wave function is not particular symmetric. The flux shift is same, but almost orthogonal to its particular conjugate partner. And we have shown that it captures topological order of this new phase. And F is attributed to experimentally observed 2.5 unit of thermal Hall conductance. However, this is not rigorous. We just from seeing the wave function form, we might think that there is a G2 symmetry. You will have one Majorana mode that can give you 2.5. So more work is needed for confirming that it will be 2.5 unit of thermal Hall conductance. And we find that A phase is not only for 5/2 states, it's actually robust for all the observed quantum Hall states in the second Landau level. So in that phase, in that regime, kappa 1 to 2, all the observed states are possible in the second Landau level. And it is most likely that the observed fraction quantum Hall states in the second Landau level are the states in the A phase. So that is our final conclusion, that whatever states we are observing in the second Landau level that corresponds to the A phase. A phase means the phase of kappa in this regime, 1 to 2. Okay, so with that, I invite.
Thank you very much. Questions? Okay, there's Kirillo and there's Ankur.
A question. Since the wave function is just a Pfaffian shifted by some flux, naively, I would perhaps expect the same set of edge excitations, or maybe not. You're saying it has different properties. Do you have an idea what would be the edge theory of this new phase?
Yeah, so that was our age prediction is. So for 5 hours half state is you have, I mean, these two modes are for the, okay, there's another, two modes are fully filled and all so you can ignore that. So you have one forward moving mode, E/4, one backward moving mode, which is minus E/4, and another Majorana-like mode.
Intuition, why specifically this edge structure?
Yes.
Some intuition.
Yeah. So you can see the wave function here. So if you, let's see. So this is power 1 to all electrons. And then you make two groups. One is n by 2, n by 2, n by 2. And there is a power 2 when there are two different groups. The same group, there is no power. So you can have the matrix like K matrix 1, 3, 3, 1, because the power for the other group is 3, and the same group it is 1. So this is the K matrix that we have analyzed. And by analyzing that, we have found this, that quasi-particle charge is 1/4. Eigenvalue of this, one positive and one negative, that gives one forward and one backward moving modes. And so that's why this is these two modes. And we have considered now a hidden symmetry here, because you have a n bosons. I mean, bosons mean you have this factor out. You can think about the bosons. So these bosons have to choose two groups. Each boson can choose two groups. It has the option to go here or there. So some kind of hidden G2 symmetry is there. So we believe that.
And that's the Majorana mode.
Yeah, we believe that that is Majorana mode, but I have no rigorous proof of that. That will be.
I see. I cannot disprove you. I want to point out that Pfaffian would be similar just with the K matrix 3, 1, 1, 3. I anti-symmetrize, I get Pfaffian. So, and by your logic, you would get there E/4 two modes, but we know that Pfaffian has just one charged mode and one Majorana. So maybe this logic about how to identify the modes requires refinement. I would seriously look into the analogy with Pfaffian.
Yeah, what are you suggesting? What will be this matrix here?
If you take 3s on diagonals and 1 out of diagonals.
Yeah, 3, 1, 3,
and
1, 3,
3, 1, 1, 3, yes.
Right,
3, 3, 1 Halperin.
Yeah, those have, yeah.
And you anti-symmetrize the wave function, you get exactly Pfaffian. It is
yeah.
known.
Yeah, so that has, yeah. So, but the Pfaffian itself has a Pfaffian factor, which gives you the Majorana. And
this,
then,
after anti-symmetrization, that will give you exactly the same Pfaffian factor. So kind of, if it's one species, if there is no microscopic internal number, one has to anti-symmetrize the wave function,
yeah.
And that kills some degrees of freedom that naively would be there. We can talk later.
Okay, sure.
Yes. So one thing I wanted to ask that you mentioned that the Majorana that you predict, you have drawn it to be actually downstream. But if it is a flux shifted Pfaffian, I wouldn't expect my thermal conductivity to change, right?
What are you suggesting?
So the thermal conductivity of Pfaffian is 3/2, right?
Pfaffian is 3/2 or 7/2, I think. Pfaffian is 7/2.
Fine, 7/2. But I'm saying that why would I expect it to change if it's just a flux shifted wave function?
No, this is not flux shifted wave function. This is completely different wave functions. Okay, different. So talking about the wave functions, it has a structure to G2 mode. So Pfaffian also has G2 mode. That's why gives you forward moving Majorana mode. So I'm also suggesting that wave function have a forward moving Majorana mode. But here, so Pfaffian has only one forward moving mode.
Yeah, I understand. Yeah, you have two of them, and you can have this.
Two are the backwards, one forward and the other backward.
Yeah, and they have carry opposite, like it's a whole like
Yeah,
current.
like,
So,
right.
so you should think of them actually really co-propagating modes.
Yeah, so
in
yeah,
that-
so
that
so
language.
that's all. Yeah, so you can.
That I understand.
Yeah, so
But I'm saying that what is the reason that I would think that Z2 has to be in the upstream direction? Like, what tells me that
yeah,
it,
unless so everything is upstream directions, unless it is a particle conjugate kind of things. So if all wave functions, electronic wave functions always give the forward moving thing. Like if you have the anti-Pfaffian, it gives the backward moving Majorana mode. But that is, you can think about holes. But for
I
the
see.
electrons, so this is always forward moving.
I see. I had another question about your phase diagram about this kappa I, kappa J. So what this I and J stands for? I couldn't understand
Yeah,
that.
so yeah, as yes. So you have several kappas, right? Kappa 1, kappa 2, different kappas. So I can diagonalize my Hamiltonian at kappa 1. I can diagonalize Hamiltonian at kappa 2 because they're two different Hamiltonians. So for each, I will give it two different down states. If they belong to the same phase, then their overlap must be close to 1. That's what we found here. In this phase, whenever the kappa is small, you can see their overlap is close to 1.
Maybe let me ask the question. No, that I understand. I'm asking what this I and J run over. Like, is it for any I? First of all, what is this
so
I and J
kappa
run over?
I, so kappa I is, let's say, 0.1, kappa 2 is 0.5.
No, what is I and J? Like I and J is 1, 2, 3, 4, 5.
Yeah, 1, 2, 3, 4, 5. Value of kappa.
And it is for any pair of kappa. This is true?
Right.
Arbitrary I and J combination.
Right.
I see.
Yeah, when they are in this range.
I see. Now I understand. And I have a very small comment. So at the very end, you mentioned that this A phase shows up in the second Landau level for all kinds of quantum Hall phases.
Yes, all.
And a corresponding point that you made is that then probably all the thermoconductances of all of the states has to be equal.
Yes.
I think it has been seen that it is not equal when you interface with an n equals to 2 or n equals to 3.
Possibly, I don't know.
I'm just telling you a fact. It's just a comment. Yeah. Thank you.
But it's not probably still not come out in paper for that. Yes.
Yes.
For which state?
I think they had the 2 plus 1/3, and I think also another one, some other phase.
Okay, 2 plus 1, there is a history. I have studied 2. I have studied it's possible 2 plus 1/3, but 2 plus 1/3 actually compete with some abelian state. Abelian state. So there is a now energetically you have to compare. There is a possibility of these states possible. In the A phase, it is possible. Now there is a competing state. There is a Laughlin state also is competing with that. It's probably for 1/3. Actually, the Laughlin state wins. Okay, so that would be again.
Yeah, they saw the Laughlin state.
I guess if you do for 2/5, so my guess is that it will be 5 up.
I don't remember that they had the 2/5 or not, but we can talk offline. Yeah, we can talk offline. Thanks.
So just I'm very surprised. How does it make sense that you have a counter-propagating 1/3 mode, charge mode, and any amount of disorder should gap it out? So I would imagine that in an experiment that those counter-propagating 1/3 mode will gap out.
So counter-propagate, you can have a mode like this and another maybe counter-propagate.
No, the first picture you have.
Yeah, this is things. So these things can be converted like this. So if you have a particle moving and they're probably neutral, like you have a 2/3, a normal lowest Landau level 2/3. You have a forward moving and backward moving, and then
but they are not of the same this thing. Here you have exactly 1/4 each.
So yeah, 1/4 each.
So there nothing will be left. I mean,
2 over 4.
Oh, I see. Okay, fine. That makes sense. Okay, fine. Thank you.
Otherwise, star will not.
Yeah, I mean that's I'm confused.
Other questions? Hey, there are no other questions. Let's thank Sudhanshu and all the speakers.